Hello everyone, my name is Caiman Gonçalves and I will talk about the vector resonance spin alignments as a proof of spin hydrodynamics and freeze-out. This is my outline and I will give you a brief introduction to heavy ion collision and I will explain the summary result using S3 group and coalescence model. In the last I will explain the conclusion perspective of this work. So this cartoon represents the some states in relativistic heavy ion collision. The first one is the represent the collision between two nuclei with relativistic velocity. In the next stage, we have the pre-equilibrium, and the summary certainty time we have the quark-gluon plasma and hydrodynamic expansion. With the decrease of temperature, we have the hadronization, that is the particle formation. And finally, we have the hadronic phase and the freeze out. We can detect this particle in this stage. So, in peripheral collision is make in fireball the high angular momentum. This high angular momentum creates inside the quark-gluon plasma the vortices. These vortices are represented from this arrow yellow. This vortex coupled with the spin of the quarks make the final stage in heavy ion collision particle polarized. The polarization is the first created in the reaction plane direction, but the transversion expansion makes vorticity in the longitudinal reaction too. So the first evidence of vorticity related to the particle polarized was published in Nature for gold-gold collision for lambda and anti-lambda baryons. The principal idea is that the high angular momentum creates vortices inside the quark-gluon plasma. These vortices couple with the spin of the quarks and making the final stage in heavy ion collision particle polarized. The polarization is referred to the fermions is measured via weak decays, but the spin alignment is referred to spin 1 mesons is measured via parity conserving strong decays. So we don't know whether the spin is aligned or anti-aligned with the measurement, but now we'll talk about more the vector mesons. So how to measure the alignment is measured from this equation, and this represents the angular distribution particle. This is coefficient is the density matrix coefficient. The specific coefficient is called the alignment factor. So this is the variable make the connection with the density matrix coefficients, and this theoretical uncertainty is what you can learn about the particle production model using the alignment in quark-gluon plasma. It's possible learning about the two particle models that are the Copperfield model. That is the principal hypothesis is the spin and vorticity are in equilibrium. This means that the density matrix is a not coherent state. But in the case of the coalescence model, we have the principal hypothesis is the spin and vorticity are not in equilibrium. This means that the density matrix is a coherent state. Now, in this work, we will study this density matrix for using the S3 group because for the spin 1 particle, the density matrix for spin 1 particle is an element of the S3 group. So, and using the density matrix from the S3 group, we have this density matrix, and this density matrix contains 2 qubits, or more exactly, a qubit of information that the principal idea that use the density matrix from SU3 group is using the density matrix from SU3 group gives us the opportunity to obtain more information about the thermodynamic equilibrium between spin and vorticity and the state coherence. Make the transformation to the library frame, we have this equation. From this density matrix, we can obtain this following system equation. From this following system equation, we can make the connection between the experimental values with the model values. Using the coalescence model, because combine the angular momentum of vorticity with the spin of the quarks in the spin space. So from the coalescence model, we have this density matrix is given by this equation. Here we have the capital omega represents the vorticity early collision. This omega represents the vorticity transferred to the meson and at the hydrogenation state. This makes the rotation, the direction of the spin direction to the vorticity. This is make the transformation to the library frame. In the last, this is the represent the Clebsch-Gordan coefficients. Make the average of a Gaussian eigenfunction of coalescence angles. We have the following density matrix. This angle represents the angle between the spin direction and the vorticity. From this equation, we can obtain these following coefficients. And this L represents the angular momentum of vorticity transferred to the meson at hydrogenation state. So for the L equal to 1 and L equal to 2, we can see that it is approximatively cancel themselves for these three coefficients. This shows that this is the three coefficients is not sensible for different contribution of angular momentum. But these two coefficients are sensible for the different contribution of angular momentum. This is shows that the good way for the measure experimentally the different contribution of angular momentum. So this angle theta r and phi r, just theta r was measured, but the phi r would give us more information about the spin alignment. This is my conclusion and perspective. The conclusion is, if spin and vorticity are in equilibrium, one expects that Cooper phi is a good estimate. But if spin and vorticity are not in equilibrium, so coalescence model is a good estimation. This means that the density matrix is a coherent state for some choice N3, N8, and these angles. The next step is to use a numerical code that to solve a diffusion equation coupled to the hydro output. So thank you for attention.